Welcome back. So, in the last lecture we solved a couple of problems on earth pressure theory. So, today we will be taking a few more problems on earth pressure theory. Okay. So, the first problem is the problem says that a 5-meter high rigid retaining wall has to retain a backfill of dry cohesionless soil having the following properties such that phi is equal to 30 degree, void ratio is equal to 0.74, specific gravity is equal to 2.68 and Poisson's ratio is equal to 0.36. So, first thing is plot the distribution of lateral earth pressure on the wall. Second is determine the magnitude and point of application of the resultant thrust, and third one is compute the percentage change in the lateral thrust if the water table rises from a great depth to the top of the backfill. Okay. So, this is the problem. So, problem says that a 5-meter high rigid retaining wall has to retain a backfill of dry cohesionless soil having the following properties: phi is equal to 30 degree, E, that is the void ratio, equal to 0.74, specific gravity G s equal to 2.68 and the Poisson's ratio mu equal to 0.36. Plot the distribution of lateral earth pressure on the wall. Okay. So, and the second is determine the magnitude and point of application of the resultant thrust, and third one is compute the percentage change in the lateral thrust if the water table rises from a great depth to the top of the backfill. Okay. So, these three things we are supposed to find out from the problem given. Now, coming to the solution. Okay. So, first we need to find out the bulk density of the backfill, right. We know the specific gravity, we know the void ratio, from there we can find out the bulk density of the backfill soil. So, bulk density of the dry backfill is equal to gamma b is equal to G into gamma w divided by 1 plus C. So, this expression you know from the basic definition of your bulk density. So, from this I can get bulk density is equal to 15.4 kilonewton per meter cube. Okay. Now, as the wall rigid, because if the wall is rigid, that means there is no movement in the wall. So, if there is no movement, then what kind of earth pressure you are expecting? So, earth pressure at rest condition. So, as the wall is rigid, the lateral pressure exerted by the backfill is earth pressure at rest, right. So, this is rigid retaining wall. So, that means there is no movement of the wall is happening. So, it is completely firm at the location where the wall is fixed. Okay. So, therefore, coefficient of earth pressure at rest can be found out by K naught. So, what will be the expression for coefficient of earth pressure at rest condition? So, K naught is equal to mu by 1 minus mu, that already we have seen in the lecture part, right, mu by 1 minus mu, and that is nothing but equal to 0.36 by 1 minus 0.36, which comes around 0.5625. Okay. So, at the top of the wall, that means Z equal to 0, P naught is equal to 0, right. We are considering earth pressure, we are considering rigid wall. So, therefore, whatever pressure you will be getting, that is earth pressure at rest condition. So, at top of the wall, what will be the pressure? That is P naught is equal to K into Z, sorry, not K, K naught, basically that is nothing but earth pressure at rest condition. So, coefficient of earth pressure at rest condition is K naught. So, the P naught is equal to K naught into Z. So, at Z equal to 0, that pressure, earth pressure at rest condition or the lateral pressure is simply 0. Okay. So, at the bottom of the wall, that means Z equal to 5, your earth pressure is equal to K naught gamma into Z. So, which gives me 0.5625 into 15.4 into 5, which comes around 43.3 kilonewton per meter square. So, the distribution of lateral earth pressure is shown as so this is the wall, okay. The total height of the wall is say 5 meter, and your lateral earth pressure is shown here. So, that is 43.3 kilonewton per meter square at the base. Okay, 43.3 kilonewton per meter square per meter run of the wall. Okay. So, therefore, the first part is over. The first part you have to find out the distribution of lateral earth pressure on the retaining wall. So, that already we have got it. Now, the second part. The second part resultant lateral thrust on the wall considering the unit width. Okay. So, because in one direction, that is normal to the board, your wall is having the unit, I mean infinite length. So, per unit width, okay, considering per unit width, the resultant lateral thrust on the wall will be coming as P naught, that is the total thrust, is equal to half K naught gamma B square. So, by putting the values, K naught is 0.5625, that comes around 108.3 kilonewton per meter run of the wall. Okay. So, we have got the total thrust. Now, this total thrust is acting at which point? Now, if I want to find out the point of application of this total thrust will be acting. So, this is your total thrust say, and this is your point of application. So, this depth is nothing but h by 3, right, from the base of the wall. So, I can write the resultant thrust is applied at a height of 5 by 3 is equal to 1.67 meter above the base of the wall. So, we have got the resultant force, that means capital P naught as 108.3 kilonewton per meter run, and we have got the point of application of this resultant thrust. Now, coming to the third part. In the third part, if the water table rises to the top of the wall backfill the soil will get fully submerged, right. That means, at some depth your water table was there, now water table is rising at the top of the backfill. So, the whole backfill soil will be under submerged condition. So, let calculate the submerged unit weight, because that will be required to find out the lateral pressure. So, that is nothing but Gs minus 1 by 1 plus E into gamma W. Okay. So, if I put the values, so I will get gamma prime equal to right 9.65 kilonewton per meter cube. So, therefore, resultant thrust capital P naught is equal to half into K naught gamma prime H square. So, that is due to the soil, because the submerged backfill is there. So, that is due to the soil, plus your water will give some pressure now, hydrostatic pressure, right. So, that will be half gamma W H square. Okay. So, this part is coming from the soil and this part is coming from the water. So, that is the total thrust now acting on the wall. So, if I put the values, so half H square into gamma prime multiplied by K naught plus gamma W is equal to 192.8 kilonewton per meter run. So, therefore, percentage increase in lateral thrust is equal to 192.8 minus 108.3 by 108.3 into 100%. So, that comes around 78%. So, you are getting 78% increase, okay, on the lateral thrust once the water table is rising up to the top of the backfill. The second problem says, problem say 27, what is the total active force per unit width of wall and what is the location of the resultant for the system shown in figure. Use Rankine equation for smooth wall. Okay. The total depth of the wall is 7 meter. Now, the backfill is having two layers. The top layer, which is having the depth of 3.5 meter, which is having the property of phi 1 equal to 32 degree and gamma 1 equal to 16.5 kilonewton per meter cube. Okay. You have the surcharge Q, which is equal to 100 kPa. Okay. So, this is your soil 1 and you have the water table which is at this level, okay, at the mid depth of the wall. This is your ground water table and the soil 2 which is having the property phi 2 equal to 30 degree and gamma 2 equal to 19.25 kilonewton per meter cube. This is your soil 2. Okay. So, this is the problem. So, for this type of retaining wall, you need to calculate the total active force, that means active thrust, okay, per unit width of the wall and the point of application of that active thrust. Okay. For this type of problem, let's see how we can solve this problem. Now, solution. First, you need to calculate the active earth pressure coefficient for both the layers, because now you will be getting different earth pressure coefficient, active earth pressure coefficient for different layers, because soil 1 is having phi is equal to 32 degree, whereas soil 2 is having phi is equal to 30 degree. So, you will be getting different active earth pressure coefficient at different soil layer. So, your Ka1 is equal to 1 minus sin phi 1 by 1 plus sin phi 1. So, which is coming, so phi 1 is equal to 32 degree as given in the problem. Okay. Similarly, Ka2 is equal to 1 minus sin phi 2 by 1 plus sin phi 2, which comes as 0.333, where phi 2 is equal to 30 degree. Okay. Now, at z equal to 0, that means top of the wall. At z equal to 0 means top of the wall. If I consider, we have P1, that is the, what is P1? P1 is the active earth pressure at the top of the wall. At that level, what is the active earth pressure acting? So, what should be the magnitude for of P1? Any guess? So, P1 is nothing but the that will be completely contributed due to the surcharge of the soil. So, because the soil is, I mean, at z equal to 0, your active pressure from the soil is not coming into the picture, right. At z, at top of the wall, you see you do not have any kind of active pressure, because it is purely cohesionless soil, it is not the cohesive soil. So, you will not be getting any pressure exerted by the backfill soil at the top of the wall. So, what will be only remaining? So, the remaining part will be the surcharge, due to that you will be getting some active earth pressure at the top of the wall. What is that magnitude? Ka1 into Q. Okay. So, Ka1 you know 0.307 and Q you know 100. So, you will be getting 30.7 kPa. Okay. Now, at the interface of top stratum, Z1 equal to 3.5 meter, that is just at top of interface, the vertical stress, just top of interface means, so interface is happening at the depth of 3.5 meter, interface between two layers. Okay. So, soil layer is extending from z equal to 0 to z equal to 3.5 meter, and soil 2 is extending from z equal to 3.5 to z equal to 7 meter, right. So, at the interface we are considering what is happening at the interface, let us see first. So, at the interface of top stratum, that Z1 is equal to 3.5 meter. So, interface is happening at 3.5 meter depth below the ground surface, that is just at top of interface what is happening we are going to find out, and then we will be finding out just below the interface what is happening, and then basically if there is some change at the interface, abrupt change, that means just on the top you will be getting something, just at the below, at the base or at the below of the interface you will be getting something. Okay. Just below the interface you will be getting something. So, anyway, so just at top of interface the vertical stress is nothing but sigma z is equal to q plus gamma 1 z1. Okay. So, what is your gamma 1? Gamma 1 is 16.5 kilonewton per meter cube, that is given in the problem, and z1 is equal to 3.5. Okay. So, q plus q, of course that is there, that is the surcharge, that will be there for the whole deposit, right, that will be constant, that is constant surcharge, plus gamma 1 into z1. So, if I put this, so 100 plus 16.5 into 3.5. Okay, this is your sigma z at the top of the interface. Please remember that is just at the top of the interface. So, therefore, P2 at that level, what is your active earth pressure? At that level means just at the top of interface what is the active earth pressure. So, P2 is equal to Q plus gamma 1 Z1 into K A1, right, vertical pressure into earth pressure, active earth pressure coefficient. So, that gives me 100 plus 16.5 multiplied by 3.5 into 0.307, that comes as 48.4 kPa. So, basically say 3.5 meter, 3.5 meter. Okay. So, this is your 30.7 kPa, okay, and you have got P2 equal to 48.4 kPa, where it is acting just at the top of the interface. So, this is your 30.7, the total is 48.4. So, therefore, this remaining is 17.7. I am not writing kPa everywhere. So, this is quite understood that everywhere it will be kPa, that is the pressure diagram. Okay. So, this is the pressure diagram at the top of the interface. Okay. So, at the top of the wall you have the pressure at 30.7 kPa, which is due to the surcharge, exclusively for surcharge, and then at the base at the just at the top of the interface you are getting 48.4, just we have calculated. So, 30.7 plus 17.7. So, that is the total pressure acting at just at top of the interface. Okay. So, now continuing for soil 2, at depth just below the interface, that is Z2 equal to 3.5 meter, right, 3.5 meter. We are into soil 2, and since that is the location of the groundwater table, we will have to use gamma prime, which is nothing but 19.25, and here I am using gamma w equal to 9.81, which is nothing but 9.44 kilonewton per meter cube. So, basically interface is the problem. So, just top of that, the top of the interface you are in soil 1 region, just below the interface you are in soil 2, right. So, just above or just at the top of the interface already we have calculated the pressure, and that pressure diagram looks like this. Okay. Just below the interface, basically you are entering soil 2, but still you are at the interface. So, physically Z equal to 3.5 meter, right. So, just top and just below the interface we are considering. So, just below the interface you still have Z equal to 3.5 meter, and that is the location, because the interface is the location of the groundwater table, and groundwater table should be considered just below the interface, because just at the top of the interface there is no effect of water, right. So, just below the interface you are getting the effect of water. Okay. So, therefore, the soil 2 should be considered as submerged condition. Okay. So, just therefore, just at the interface, that means interface below the interface, your P2 prime will be equal to Q plus gamma 1 Z1 up to Z, where Z equal to 3.5. So, that contribution is coming from soil 1 plus gamma Z Z2, where Z equal to 3.5 into Ka2. Okay. So, Z1 means Z1 is the Z which is varying within the soil 1, and Z2 which is Z which is varying from in the soil 2. Okay. So, now in this expression you can find out P2 prime is equal to, just below the interface your P2 prime will be equal to Q, that is 100 plus 16.5 into 3.5, that is coming from, that is the contribution, that is the vertical pressure at the interface due to the soil 1, okay, plus what is the vertical, this gamma prime Z2 at the interface, because Z2 is 0 at the interface, because we have not yet entered soil 2 properly, just below the interface we are there, okay. So your Z2 is 0, so 9.44, that is gamma submerged into 0 into Ka2. Understood the concept? I mean, if you understand the concept, then it is very simple, okay. So at the interface you have got two different condition, so just above the interface, just below the interface, okay. So from this I can get P2 prime is equal to 52.5 kPa. Now what does it mean? So you have got P2 which is equal to 30.7 plus 17.7, right, when you considered from top to the interface up to the interface. Now you are considering just below the interface and you are getting P2 prime. So you are getting basically a sudden jump in the lateral earth pressure, okay. So we can write down that we have an abrupt discontinuity in the pressure diagram of 48.4 kPa and at 3.5 plus dz, that means you are in soil 2, but you are at interface, okay, a pressure of 52.5 kPa, okay. So that means you are getting some abrupt discontinuity, abrupt change, okay, some 48.4 to 52.5. So this up to this point is 48.4, then say 52.5 is happening here, say for example. Say this is the point where you are getting 52.5, okay. At the interface both the things are happening due to the abrupt discontinuity, okay. Now at the bottom of the wall, what is the pressure? At the bottom of wall, your P3, that is pressure, is equal to 100 plus the vertical. So first that this within the bracket whatever we are writing, that is nothing but your vertical pressure plus the vertical pressure due to your soil 1 plus the vertical pressure due to your submerged soil 2 into Ka2, that is nothing but your P3, which is acting at the base of the wall. So if you put the values, you will be getting P3 is equal to 52.5 plus 11 is equal to 63.5 kPa. So basically this is your 11, okay. So you are getting the pressure at the base of the wall as 63.5. So 52.5 plus 11 is nothing but 63.5. So, this additional part will be 11 kPa, okay, as I wrote there. Okay. So, the water also contributes lateral pressure, okay. So, therefore, Pw is equal to gamma W into Zw. So, what is your gamma W? 9.81, and what is the total depth of water? That is 3.5 meter is equal to 34.3 kPa. So, the water pressure, pressure due to the water will be 0 at Z equal to 3.5 meter, that means where the groundwater table is getting started, and you will be getting water pressure is equal to 34.3 kPa at Z equal to 7, that means at the base of the wall. So, from there I can get the pressure distribution for water. So, this is your 34.3. So, I will be getting the thrust, say this is your P1, this is your say P2, this is your say P3, this is your say P4. Okay. So, now if I calculate P1, P2, P3 and P4, so P1 is nothing but the area under this rectangle, P2 is the area under this triangle, P3 is the area under this rectangle, and P4 is the area under this whole triangle. Okay. So, if I find out P1, P2, P3 and P4 from this diagram, from the area of this diagram, then the summation of P1, P2, P3 and P4 will be the total thrust acting on the wall, and if I want to find out the point of application of that resultant force, then we have to get the individual point of application of those forces, right. So, next what we will do, now to obtain point of application of resultant force R, we have R into capital Z bar is equal to summation of Pi into capital Zi, where capital Z is distance from bottom of wall. Okay. So, now let us calculate all the forces individually. P1, what is P1? P1 is the area under that rectangle, the top rectangle. So, P1 is nothing but 30.7 into 3.5, which comes as 107.5 kilonewton, right. Now, why it is acting? It is acting at the mid depth of this rectangular part. So, from the base, what will be the distance? 3.5 plus 3.5 by 2. So, your Z1, so your capital Z1 is equal to 3.5 plus 3.5 by 2, which comes as 5.25 meter. Similarly, I can find out P2, which is nothing but 17.7 into 3.5 by 2, that is the area under this triangle, 17.7 into 3.5 by 2. So, that comes as 31 kilonewton. And what will be Z2? Z2 is the capital Z2 is the distance from the base of the wall to the point of application of P2. So, that is nothing but 3.5 plus 3.5 by 3. So, that comes as 4.67 meter. Similarly, I can find out P3. P3 is 52.5 into 3.5, which comes around 183.8 kilonewton, and your Z3 is equal to simply 3.5 by 2. What is P3? P3 is the this area, okay, area under this rectangle. So, 3.5 by 2, which is nothing but 1.75 meter. So, now include water with P4, since both areas are triangle. So, we are considering this triangle and this triangle. So, there is this is the whole triangle which will give me P4. So, P4 is equal to 34.3 plus 11 into 3.5 by 2. Agreed? So, that is the area of the whole triangle. So, that comes around 79.3 kilonewton, and Z4 is equal to 3.5 by 3, which is equal to 1.17 meter. So, the resultant force, resultant thrust R is equal to summation of Pi, which is equal to, so P1 plus P2 plus P3 plus P4, if you do that, you will be getting 401.6 kilonewton. So, that is one of the answer. Okay. Have you got it? So, this is the total thrust acting on the wall due to this layered backfill, and the point of application of this R is, I will get it. So, point of application of this R is R into Z bar, capital Z bar, is equal to summation of Pi into Zi, as I have written earlier, right. So, R you know, so from this I can write 401.6 into Z bar is equal to summation of, so 107.5 into 5.25 plus 31 into 4.67 plus 183.8 1.75 plus 79.3 into 1.17. So, from this I will be getting Z bar equal to 2.80 meter above the wall base. Okay. So, this is your resultant force R and this is your point of application of the resultant force, that is 2.8 meter above the wall base. Okay. So, I will stop here today. So, in the next class we will take a few more problems on the earth pressure theory, and then of course, we will be solving some problems on the stress distribution and so on. Thank you very much.